great pleasure to introduce Professor Zhang from Stanford, who started with his undergraduates at Free University of Berlin and has his PhD from Stony Brook, and now Professor Stanford. And he will tell us about a really exciting development in condensed matter physics this year.
Okay, thank you very much. Shall we dim the light a little bit more?
I think you can do it with this device. Let's see.
Oh, good. Thank you. So it's a great honor for me to come here to University of Stockholm and give a colloquium here. So today I'd like to talk about some very recent development in the field of condensed matter physics, quite a relatively new effect called the quantum spin Core effect. So this is the work done based on a paper we wrote in Science last year, and it's a theoretical prediction, and now it has experimental observations. So I assume I already gave a relatively specialized seminar to condensed matter audience, so I assume quite a number of people here are not condensed matter physicists, so let me first spend a few minutes advertising a little bit for my field. So in chemistry, of course, the thing people were looking for are search for the new elements, and that led to a golden age of chemistry, and led to the discovery of the periodic table, which gives a fundamental organizational principle of elements in chemistry. And that's kind of started in the last the century before, and was, of course, a glorious search which led to glorious success. Now, in the 50s, then there was the search for the particles, new particles in particle physics, and that was kind of the holy grail of that field, and that, of course, was also tremendously successful and led to the golden age of particle physics. Now, what is the kind of the holy grail of this field we work on, called the condensed matter physics? So in condensed matter physics, we are looking for new states or fundamental states of matter. So, for example, in the classical world, we know that the same H2O molecule can form three different states: the ice state, the water state, and the vapor state. So when you take it apart, it's not very interesting. It's the same H2O molecule. But the interesting thing is how they organize themselves together. And they can only organize themselves into these three forms of states in the classical world. And that gives the notion that is captured by one sentence by Phil Anderson called "more is different." When you simply have the H2O molecule, it's the same H2O molecule. But when you put lots and lots and lots of them together, they can organize themselves very differently into different states of matter: solid, liquid, and gas. So this is the kind of atoms of our field. The atoms of chemistry are the elements, kind of the fundamental building block of particle physics are the new particles. But in condensed matter physics, these are the fundamental states of matter. And we would like to look for them, classify them, to find whether there's a principle to organize them similar to the periodic table. Now, in the quantum world, things get a lot more interesting, and there are a lot more states of matter. We can have metals, we can have insulators, we can have superconductors, and we can have magnets. So, for example, this is a crystal structure of silicon, and that's, of course, very useful in all solid-state electronic devices. This is the picture of a magnet, and this is the picture of a superconductor. And the underlying properties, they all come from the electrons, but yet they are organizing themselves in a dramatically different way and different fashion. Okay? So now, just like we have an organizational principle for the elements, namely the periodic table, we would like to think about some organizational principle which classifies and help us to understand these different forms of matter. And basically, through the research starting in the 60s, we have now such a principle, and that's called the broken symmetry principle. So basically, when you look at all these forms of matter, they always, every different state of matter, that you can call them to be different, they always break the symmetry in a unique and different way. So in a sense that all these states are differentiated by the broken symmetry. For example, the fundamental interactions between the atoms are totally translationally invariant. If you let a pair of atoms interact here, it's more or less the same as how a pair of atoms would interact when you shift their center of mass into a different place. But once you live inside a crystal, the translational symmetry is broken, because if you shift a little bit, it will be different from shifting by one unit cell. So a crystal basically is described by the broken translational symmetry. Now a magnet similarly breaks the symmetry. Now if you have a north pole and south pole, in the world of basic interaction, let's say everything comes from the Coulomb interaction of the electrons, but which are totally rotationally invariant. But once you form these magnets, then of course north becomes different from the source. So the rotational symmetry gets broken. And that's the symmetry that's broken inside the magnet. Now, we also have superconductor. The symmetry that the superconductors break is a little bit subtle to explain. Basically, it violates, in a sense, the particle number conservation. If you shoot in some electrons, it can come back as a whole. So it looks like the number conservation law is broken inside a superconductor. Now, this is really a profound understanding, and it's a understanding which came from condensed matter physics originally, but had profound implications beyond condensed matter physics. For example, a key ingredient of the standard model for weak interaction rests, or the Higgs mechanism rests, on the understanding of the broken symmetry. Now, so I said, I basically told you this rather happy status that we basically have a periodic table. We have a principle, namely the principle of broken symmetry, which help us to classify all those states. And basically, when you look at states in condensed matter, basically 95% of the states fall into this category and can be classified this way. But then in the 80s, a remarkable discovery in condensed matter physics, and the quantum Hall state has been discovered. And I'd like to explain to you that this is the first state discovered that does not fall into the previous category. And in many sense, it's more interesting. So basically, it's a junky looking kind of material, which has this, it's basically two-dimensional, formed out of some interface of semiconductors. And you make some contact, you apply a magnetic field, and then you just measure resistance as you usually would do. And the remarkable discovery is that when you measure in the presence of a magnetic field, there's a Hall resistance. If you pass a current this way, you can measure a voltage transverse to the direction of the current. And when von Klitzing did this experiment, he found this very interesting trace, the celebrated quantum Hall trace. And so basically, when you look at the resistance, the Hall resistance, or the conductance, it has a fundamental unit. E squared over h. When you convert that into resistance, h over e squared, it's roughly 26 kilo ohm. It's a kind of a resistance unit formed out of fundamental constants of nature, the electric charge and the Planck's constant. But then interestingly, the coefficient in front of it is always an integer. And that's characterized by these various plateaus. Plateaus means as you change magnetic fields, this value does not change. And that equation holds true to a remarkable degree of precision, 1 part in 10 million, and even maybe more precise now. Okay? So now, very soon after this discovery, Laughlin, my colleague at Stanford, gave a very nice explanation. But then very soon after, it was realized that the reason this number is very precisely quantized has a deep topological reason. Basically, if you measure the whole conductivity or whole conductance in the right unit, it's basically a topological number called the Chen number. And that was discovered by David Fowlers and his co-workers. So now I will not have the time to explain you all the details of what this equation means, but I would rather give you simple elementary examples. So, for example, if you just learned about calculus and you learned how to do integrals, and then you do some integrals. Usually, if you do an integral, the value of the integral depends on the integrand. if the integrand is a different function, you will get a different integral out of that. But consider a very simple integral of this form, a one-dimensional integral over x, and x lives over a period of between 0 and pi. But then this integrand is a derivative of some function. So now in this case, kind of the derivative and the integral kind of cancel, and this integral only depends on the boundary value. But if this is theta is an angular variable, it would have a constraint that e to the I theta always has to be equals to 1. And that means that when theta comes back to itself, it can only change by integral units of 2 pi times integer. So therefore, no matter what kind of theta, so there are infinitely many theta functions that you can stick into this integrand. As long as it satisfies this boundary condition, the outcome will always be an integer. So this is a rather unique situation, right? Most time when you do integral, the value of the integral depends on the integrand. But here it does not. Well, it does depend on the integrand, but it only depends on the integrand to some integer modulo some integer. And if you within this integer class, there are many functions that are different, but the integral always comes out to be the same. So it is this kind of integral which we call a topological invariant. And of course, mathematicians, they like to classify topological manifolds and so on, and they like to come up with such mathematical expression. And when you do it for one kind of objects, you find it is 0, and for another kind of objects, which will turn out to be non-zero, and for those that are non-zero, they call it topologically non-trivial class. And that is a profound connection for the first time established in condensed matter physics, that a physically measurable quantity is directly related to a topological invariant. And in that very precise sense, the quantum Hall state is the first topologically non-trivial state of matter ever discovered. And up until recently, there's no another examples of that. And that kind of is the thing we would like to search for, because we believe nature is not just accidental. It will just not give us one and then it stops there. So maybe there are other interesting topologically non-trivial states out there. So the basic idea is that we're looking for these kind of new states of matter. A very broad class is already kind of understood. There are many details which are not understood. This class is classified by broken symmetry, and we more or less understand the basics. There are a lot of things we don't understand quantitatively. But another kind of outlying class is that these are topologically non-trivial states, and quantum Hall is the first example. So now we would like to generalize this notion of quantum Hall, and maybe by searching for some generalization, we will discover another topologically non-trivial state, and that could be very exciting, and I hope I motivated that. So let's remind ourselves a little bit, what is the quantum Hall effect? So you basically have a two-dimensional system, and you have an external magnetic field, which is perpendicular to the two-dimensional system. And when you try to pass a current along this direction, then we know from elementary physics there's a Lorentz force. So the Lorentz force will be bending the orbit of the electron. And in this case, when the electrons are bent, you see I will get more electrons accumulated on the left side than on the right side. And that is the notion of a Hall voltage, because I have accumulated a charge, and in equilibrium, this leads to a transverse voltage in a direction perpendicular to the current flow. And that is, of course, the original discovery of Hall effect. Actually, very soon after Mr. Hall discovered the Hall effect, he also discovered something similar and related, and that is called the anonymous Hall effect. It turns out that there's also a symmetry at work for the Hall effect, because the magnetic field breaks the time reversal symmetry. And you can actually prove mathematically that you can only get a Hall voltage when the time reversal symmetry is broken. But we don't need just to break the time reversal symmetry by magnetic field. For example, if we have a magnetic material which spontaneously breaks the time reversal by forming a magnetic moment, it similarly breaks the time reversal. And in that case, a similar thing happens. Then when you pass a current through, then the electrons will be bent to the left and to the right, but it will be bent more to the left than it is to the right. And that is called the anonymous Hall effect. It's rather anonymous at that time because you're not applying external magnetic field. You just only have a magnetic moment. Now you may wonder what is the kind of the microscopic reason, because it looks like without the magnetic field, there will be no Lorentz force. Why would the particles choose to bend more one way than the other? It turns out that there's a fundamental interaction in solids, and that is called a spin-orbit interaction, and that is responsible. That when you, for example, if I'm turning this way, then I have an orbital angular momentum out of the plane, and that prefers then the upspin. If I'm turning that way, it has a net orbital momentum into the plane, and that prefers the downspin. So the spin-orbit coupling, the coupling with the orbital bending, leads to coupling to the spin degree of freedom, and that is fundamentally responsible for this anomalous Hall effect. And more recently, we actually predicted that there's something called the pure or the intrinsic spin Hall effect, in which case you don't have any breaking of the time reversal. So this is really fundamentally different universality class. You don't have external magnetic field, you don't have external, you don't have any magnetic moment. Nowhere is the time reversal broken. So then, in this case, you can sharply prove that you can, if you pass a current through, it's absolutely impossible for Bittern by symmetry for you to accumulate a voltage across this sample. But you cannot have a charge voltage, namely the net number of electrons here has to be equal to the net number of electrons there. But you can still have the situation where you have more upspin accumulated on the left than the upspin on the right. So in this case, this is called so then you can have more upspin here and more downspin there. So it leads to a net accumulation of spin rather than a charge, and that is called the spin Hall effect. And that also, as we could show, comes from the spin-orbit coupling in the solids. So in this case, as you pass a current here, you have an imbalance of the spin in the direction that's transversed to it. And even though this has been observed, the Hall effect has been observed for more than a century, the spin Hall effect has only been observed in the last 2 years. So now, we argued that the ordinary Hall effect is already pretty interesting, but we argued that the quantum Hall effect is a lot more interesting. It leads to this quantized plateau, and it's a topologically non-trivial state of matter. Then it looks very, very natural that now that we have discovered the spin Hall effect, the question is, what about the quantum spin Hall effect? And that's the main part of my talk. So now, what exactly is the quantum spin Hall effect? So let me give you a very simple cartoon picture of the quantum Hall effect first. So basically, you have, in the case of quantum Hall effect, you have an external magnetic field, and you have particles, but they can only conduct at the edge of the sample. And not only they conduct at the edge of the sample, they can only conduct in one way. So the particles run around the edge of the sample only in one direction. And that's the basic cartoon picture of the quantum Hall effect. In the bulk of the sample, there's no conduction, no current flow. And all the currents are flowing at the edge of the sample. And that's the simple cartoon picture. And that picture, when you look at it, certainly breaks the time reversal symmetry. Magnetic field breaks time reversal symmetry, and most of the case, the magnetic field also aligns the spin of the electron. So the spin is also pointing along the direction of the magnetic field, and the particles only move around in one way. So because since only move around in one way, it certainly breaks time reversal symmetry, because the time reverse of that will be moving around in the other way. But there's a very intriguing idea that you can first take the quantum Hall effect, the upspins, up magnetic field, and counterclockwise rotation around the sample, but take then its time reverse, its exact time reverse. Then the up magnetic field becomes a down magnetic field, upspin becomes downspin. What is a counterclockwise propagation around the edge of the system becomes a clockwise propagation around the edge of the system. Okay, so the blue, in a sense, a very precise sense, is the time-reversed image of the red. And so we can, of course, realize the quantum Hall effect this way or that way, because you can just reverse the direction of the magnetic field. But a much more interesting case would be that in one single system, that you have identical copies. You have both a red copy and a blue copy. Now, in that case, it would be very interesting, because then there's no net breaking of the time reversal, because the blue is exactly the time reversal of the red. So the entire system does not break time reversal. And that system is called a quantum spin Hall effect. And basically, it's two copies of the quantum Hall effect put together in a way that the time reversal symmetry is not broken. So now when you take a top view of that state, you get to a picture like this. So you have a sample of the system, and in the bulk it's completely insulating. But at the edge of the system, you can have two channels. Now in the quantum Hall effect, you only have one channel, and they go at one given edge only in one direction. But in the quantum spin Hall effect, now you have two copies. You have the up spin going around this way and the down spin going around that way. And so you have two edge channels at one given edge. So now in this case, suppose I try to pass a current through the sample. I cannot pass a current through the bulk. But by raising the voltage, let's say at this electrode over that electrode, I will be passing a current, but I will be passing an up spin current in the upper edge, but a down spin current in the lower edge. And that situation, when the current is flowing, you see that I, at the same time, get a spin accumulation because I get more upspin here and more downspin here. And that is the key signature of the spin Hall. And that's why this picture explains the name. That we have the spin Hall effect. Okay? So now in many ways, you can understand that these states are really a kind of an interesting way, a very interesting set of one-dimensional conducting states. So for example, the quantum Hall effect has this chiral edge state, and they can be viewed as a way to spatially separate the one-dimensional spinless liquid. So if I have one dimension, and if I have fermions which don't carry any spins, so then I will have a simple parabolic band. I will have a momentum, I have an energy, I will have non-relativistic fermions, so they have this typical parabolic band. But if you have such a parabolic band, and if you fill the Fermi C up to some point, then you will get a Fermi point here at the right, and a Fermi point here at the left. And these are then the low energy excitations of the system. So anytime when you construct a one-dimensional spinless fermion model, you at least have two components. You will have a right mover. So if you put electrons nearby the Fermi C here, they will move because they carry a net momentum plus. They will mostly move to the right. And if you put some electron or fermions here, they will always move to the left. So these are the left movers and right movers. And if you put some impurity into that system, they can lead to some scattering. The interesting thing that quantum Hall effect is doing is basically, in one dimension, you can now separate these two channels, the right mover and the left mover. But the interesting thing that the quantum Hall effect is doing is that it's separating them out spatially. So then in the quantum Hall effect, the right mover only lives on the upper edge, and the left mover only lives on the lower edge. And that's kind of the basic cartoon picture. So the quantum Hall, when you look at one given edge, it's only half of the degree of freedom of a spinless liquid in one dimension. So by a very similar way, you can understand what is quantum spin Hall effect, because most of the time we don't have spinless fermions, we also have spin. So you will have two copies. You have a red copy for spin up and a blue copy for spin down. So for a spin-full one-dimensional liquid, you would then have you will have four channels. You have spin up, right mover, spin down, right mover. You will have spin up, left mover, and you will have spin down, left mover. And what the quantum spin Hall effect is doing is kind of spatially separating them out into two and two. So you have, on the upper channel, you have up spin right mover, down spin left mover, and in the lower channel, you have a down spin right mover and a up spin left mover. So, and this spatial separation is very important. And you can show that no matter what kind of, how hard you work, that there's no way you can construct a one-dimensional model which only has the right mover, or you can never construct a one-dimensional model which only has one set of those states. So this blue is exact time reverse of the red. And they form, because in quantum mechanics we have a fundamental symmetry called the Kramer's degeneracy. If you have a time reversally invariant fermionic system, states always have to form pairs. So this is exactly one Kramer's pair, and this is also another Kramer's pair. And you can show that there's a no-go theorem, that you can never construct a one-dimensional model with only one set of equatorless pair without the other. And the quantum spin Hall state is doing is to spatially separate these two pairs into spatial channels. So in a very precise way, these helical edge states of the quantum spin Hall effect is kind of half of the degree of freedom of the spin-full one-dimensional liquid, or the theory that you write for the helical spin liquid is, in a precise way, the square root of the one-dimensional spin-full liquid. So now, if there are students here, I'd like to tell you a more general story that oftentimes very interesting things happen when you try to take the square root out of either in mathematics or in physics. So if you want to have a more general recipe, how do you make interesting discoveries in mathematics or in physics, by and large, a very good approach would be try to take the square root of something that looks interesting. So for example, if you took the square root of -1, you would have discovered the imaginary number, and you would have discovered a whole branch of mathematics. And Dirac was busy doing relativistic quantum mechanics, and he tried to take the square root of the Klein-Gordon equation, and then he discovered the Dirac equation, and he predicted the positron. So that's another big success of taking square root. And in particle physics, in recent years, we have even much more profound discoveries simply originating by taking square roots. For example, if you have space-time symmetry, the Lorentz or the Poincaré symmetry, when you take the square root of that, it becomes supersymmetry. And that is universally viewed as the deepest symmetry you could possibly have. It's not clear whether it's observed in nature or not. And then, if you take the square root of gravity, you get supergravity, which is the predecessor of the string theory. So what we're saying is that these two analogies of chiral edge state and helical edge state, they are following an exact tradition of taking square roots. If you have a one-dimensional spinless liquid, when you take the square root, you get a chiral edge states of the quantum Hall effect. If you have a one-dimensional spin-full liquid, you take the square root, you get these helical edge states. Now, of course, once you get very familiar with it, and you can become a little more adventurous and do some more interesting things, like, for example, taking the square root of your debit account, see if it can become imaginary. So, now we told you that this state that has been proposed, and now we come to this notion that this is really topologically distinct from a conventional insulator. So what is a conventional insulator? A conventional insulator has a valence band and a conduction band. And usually there's nothing, there's a gap. And that's the reason why semiconductor works. Silicon has a band gap about 0. electron volt. And that's how a lot of the property, the reason it's called semiconductor is because this gap is relatively small, and then you can dope a little bit here, dope a little bit here, you get p-n junction, you get all the interesting semiconductor stuff. But in this way, this philosophy of looking for new states of matter, they look pretty boring and pretty conventional. You have a valence band and a conduction band. But sometimes, even inside silicon, you can have something called a surface state. So once you have a gap, you can have actually some states inside the gap. Actually, silicon, when you cut the surface in the right way, it will have some states living inside the gap. But these states are not really, they are basically, can be related to those without any surface state. Because it depends very sensitively, for example, how you prepare the surface. And if I did it differently, and if I put some disorder, I can remove those crossings or those degeneracies. And if I do a little bit more, I will remove them even further. But then once I created this situation, you see that I still would have a region which would have a gap. And in that sense, that state is really no different from that state. So we will actually call that those states are topologically the same as the boring conventional insulator. But now we have talked about those edge states of the quantum spin Hall effect, and then you have an upspin which is dispersing positively, and downspin which is dispersing negatively, meaning you have a right mover and left mover, you have an upspin right mover, a downspin left mover, and they cross at some special points of the Brillouin zone. So at the points that cross, because they form this Kramers pair, that degeneracy is totally protected by the fundamental Kramers theorem of quantum mechanics. Right? In quantum mechanics, we taught this very fundamental theorem called Kramers theorem, and it says that in a system which has time reversal invariant and which has elementary fermions, you have to have pairs. So at this point, you have to have two states, and therefore they have to cross. So if you do things to a little bit to it, you can, for example, move that point, you can change the dispersion relation, but this point of crossing can never be avoided, unlike the case here. And if you do something even more to it, you can even move it even more, but you can never remove that degeneracy. So in a very precise sense, the conventional insulator topologically look like an ordinary ring, or ordinary band. And conventional insulator with a little bit surface dating it is just some distorted ring. If you distort it a little bit, it can come back to the original form. But the quantum spin Hall insulator is more like a Mobius strip. There's this knot that has been tied that can never be untied. Actually, it can be untied if you have two sets of them, and then you can show that you can untie them. And that's like when you have a Mobius strip and you twist it twice, it's like not twisting it at all. So just remind you the non-trivial topological property of a Mobius strip. If you have an end that you send to move forward, and after completing a cycle, coming back to the original position, it's on the opposite side of the face. So that Mobius strip is called is topologically non-trivial compared to the ordinary ring. And we say that it can never be distorted one form to the other by some smooth distortion. When topologists in mathematics talk about topologically equivalent class, they distort things. But when they say they distort, they just means you move things a little bit. You cannot take a scissor and to cut it. Now, in electronic structure, when we say we perform a smooth distortion, we mean we change the fundamental Hamiltonians a bit or a lot, but never close the band gap. Closing the band gap will be like taking a scissor and cutting that ribbon. But we're not allowed to do that. And as long as you're not allowed to do that, this state can never be distorted to that state. And in that very precise sense, the quantum spin Hall state is perhaps a second non-trivial example of a topologically non-trivial state besides the quantum Hall effect. So now the question is, how do you, this is a set of very nice theoretical idea, and how do you search for this new state? Now there was a very interesting proposal by Charlie Kane and Meili from University of Pennsylvania, and they thought it could work for graphene. Now, if you know a little bit about solid state physics, recently there has been tremendous excitement that you can make a single sheet of graphite, which is called graphene. And they proposed that graphene with Liouville spin-orbit coupling can actually work to give rise to this very interesting quantum spin Hall state. But in principle, they're correct. But it turns out that the effect is just so small that most people think it's not realistic to observe it. So now, around the same time, we also have a proposal to realize quantum spin Hall effect in gallium arsenide through some strain. But it turns out to be theoretically correct, but practically very hard to implement. So the community stood in a standstill for a while, and then we came with the idea to look for another class of semiconductors. So this is kind of the zoo of zoology table for the class of all semiconductors, plotted in a two-dimensional diagram of a band gap, how big their gap is, and what is the atomic spacing of the unit cell. So here's the lattice spacing, here's the band gap. Now you see a lot of semiconductors. And very interestingly, we also color-coded them. Now what does this color mean? This color means that when band gap is in energy, and then by the Planck-Einstein formula, you can convert energy into wavelengths. So these semiconductors, you can construct some semiconductor lasers out of them, and the color that these lasers emit is uniquely determined by the band gap. For example, here I'm holding a red laser, and that is made out of gallium arsenide, and it's close to the red spectrum. And these days, a lot of device like my computer now has a blue LED, and that's more formed by materials like in this class. So this is the space of band gap energy, and you have lots of semiconductors. So we were looking for a state out of this wide class of semiconductors which could possibly realize this very interesting new state, quantum spin Hall effect. And then we realized that out of this entire diagram, there's only one element which seems to be very unique. And that element is called the mercury telluride. So it's the same stuff that it's formed out of mercury and another element called telluride. And that red line is the zero of the band gap. So everything above it has a positive band gap, but the thing below it has a negative band gap. And mercury telluride has a negative band gap. And it is only because of this very interesting property of having a negative band gap, I will show you that this material gives us the first example, experimental example, of realizing these quantum spin Hall states. So let me give you a little bit cartoon picture of semiconductor bands. Now we start from the atomic physics understanding. So if I have an atom, you solved the hydrogen spectra, and after you've solved the hydrogen spectra, you know there's something called the S wave state, which are spherically symmetric, and then there's some P wave state, and there are 3 of them, and they look dipolar-like if you plot the wave function. So now, after you learn a little bit more, go beyond the hydrogen atom theory, you learned in advanced quantum mechanics something called the fine structure of atoms. And that talks about the spin-orbit coupling. So if the electron goes around in an atom, it will have an orbital angular momentum. But the electron also has a spin. So the orbital angular, the S state does not have any orbital angular momentum, but the P state has an orbital angular momentum. So the orbital angular momentum of the P state, which has L equals to 1, will be coupled to the spin angular momentum of the electron. And by the basic rules of angular momentum addition in quantum mechanics, you can form a state which has a total angular momentum equals to 3/2 or minus 1/2. So that state will split. And in hydrogen atom, that splitting is nothing but the fine structure of hydrogen atoms. But in most solids, especially solids with heavy elements, the splitting can be much larger. So, but anyway, you form this kind of situation. And then you just put a lot of these atoms together and they form a band. So when the S bands all overlap, they become the conduction band. And when these P bands overlap, they become the valence band. And basically all of the important semiconductor physics can be understood in this very simple cartoon picture. Now, except when we look at this material called mercury telluride, it has this little bit strange structure. That in most material, you have an S level lying above the P level. But in the mercury telluride, it has a P level lying above the S level. And that has something to do with the fact that mercury is rather heavy, and it pulls the S level more down. So it has P level above the S level. So now when you spin orbit split the P level, actually it turns out spin orbit splitting is also pretty big. So it shifts the P 1/2 level below the S level, but the P 3/2 level lies above the S level. So now when you put the chemical potential or the Fermi energy is somewhere in the middle, you have this very interesting situation that in conventional semiconductors, S level lies above P 3/2, but in mercury telluride, P 3/2 lies above the S level. And that turned out to be very, very important. So then we can construct a very simple model for those two-dimensional structure. It will consist mostly of the two S orbitals, and it will consist also of the P orbitals. But the P orbitals are very specific. It picks only the strongest spin orbit coupled P orbitals. Like when from elementary quantum mechanics, you realize that if you want to form a state of P equals to 3/2, J equals to 3/2, if I already have spin up, I would like to prefer a state with L equals to LZ equals to 1. If I form PX plus IPY, that has LZ equals to 1. Now and that makes the total 3/2. And if I have spin down, I like to make a LZ equals to -1, and that makes the state which has total JZ equals to 3/2. So it turns out it's these 4 states which are most important close to the Fermi energy. And then you can write down a Hamiltonian which describes the hopping of these orbitals. And to the lowest level, the upspin and downspin don't really talk to each other. So this 4x4 Hamiltonian, again, becomes block diagonal into 2 by 2 blocks. And so within these 2 by 2 blocks, you can again work out what is the Hamiltonian, and it takes this form. Now that you may, by that time, you may already feel pretty boring. You are doing some very simple band structure or some semiconductor. You may not that much care about. But then when you look at the continuum limit, or when k goes to a very small number, close to the center of the bands, it reduces to this form. And that got us very, very excited, because this is exactly the relativistic Dirac equation in 2 + 1 dimension, right? So you have, originally you all start from these non-relativistic electrons, but when you look at those bands with the right degree of freedom, you see that it reduces exactly to a relativistic Dirac equation in 2 + 1 dimension. So it's a very beautiful theory which emerges out of these. So actually in condensed matter physics now there's another example, namely in graphene. Graphene, the two-dimensional graphene, is also described by a relativistic Dirac equation, but with the diagonal element, the mass term, exactly equals to 0. And that will be the Hamiltonian for graphene. But it turns out that in this material, this mass constant can be tuned continuously. And what is the physical meaning of the mass? It's exactly the energy difference between the s and the p orbitals. And that becomes now a very interesting thing, right? Because it has the mercury telluride compared to ordinary insulators has this mass inversion. The s and orbital energy difference changes sign. And then in the language of the relativistic Dirac equation in 2 + 1 dimension, it tells you that there's a possibility that this mass can change sign, or at least it can be tunable. And there's a profound result in field theory, which says that the Dirac model in 2 + 1 dimension would always have a Hall constant, and that Hall constant is 1/2 times the sign of the mass. So therefore, if I can tune this mass by changing its sign, then I will have a jump of the Hall constants from 0 to 1. And that is what the theory will predict. So you can kind of understand this rather strange and rather accidental looking quantum chemistry of having S level lying above the P level in mercury tellurides could in principle have a rather profound consequence, that it can lead to a Hall effect, actually a quantized Hall effect. But this would only lead to the quantized Hall effect in the upspin block. And if you did the same thing for the downspin block, you will find that the Hall constant would also have an integer jump, but then in this case it will jump by -1 if these jump by 1. So altogether there will be no Hall effect, charge Hall effect, but when you look at spin Hall effect, which is the difference, you will immediately see that it exactly jumps at this point where the mass is changing sign. So that's why this material is very important. And you can tune this sign of the mass by making a sandwich structure of semiconductor quantum wells. You sandwich this interesting material, mercury telluride, inside the more boring material, cadmium telluride. You can use, in principle, anything. You can put cadmium arsenide, except realistically it will not work. You have to pick a boring material, but that is lattice match to the interesting material. And when you look at this table I presented earlier, there's basically only one material, and that's the cadmium telluride. So the cadmium telluride has an ordinary band structure, but it's lattice matched to mercury telluride. So now you grow this semiconductor quantum well structure, it becomes an interesting quantum mechanics problem. You just solve the quantum mechanics wave function along in this direction. So now we argue that in cadmium telluride, the band structure is normal, which has the s electrons lying above the p electron. So when the mercury telluride is very thin, you will believe the band structure will be dominated by cadmium telluride, and you will have the s level lying above the p level, or in this field theory language, the Dirac mass will be positive. But then when you make it a little bit thicker, you know eventually everything should be dominated by the behavior of mercury telluride, which has the p level lying above the s level. So somewhere there has to be a transition at which these levels would cross. And you can actually predict very precisely where this level crossing occurs, and it occurs for quantum well thickness about 6 nanometers. So then, once you grow a sample which has a thickness of 6 nanometers, then you will have inside have a negative Dirac mass, and outside, which is vacuum, is like essentially having a positive Dirac mass. So when you cut around the sample along in this direction, along the y direction, and plot the mass, it starts out to be positive outside of the system, to be negative inside the system, and then positive again. So this sample edge is actually a mass domain wall, a domain wall of the Dirac mass. And we know that a domain wall of the Dirac mass will always trap a bound state. So when you solve it's a very interesting quantum mechanical exercise you can do by solving a one-dimensional Dirac equation where the mass changes sign. You see that independent of almost anything, there will always be a bound state. And the bound state here means the edge state, and because you have both two blocks, you will have a red edge state, a blue edge state for spin up, spin down, and similarly here. So that is the reason why this material will have this interesting helical edge state once the mass is turned to be negative. And there are some more topological explanations I will not get into it. So now let me go to tell you the experimental setup. So now things get pretty interesting. We wrote this theoretical paper. We predict that such phenomena should occur. And it turns out that this material is pretty well studied, only by a few groups in the world. Actually, there's the defense industry in the United States, there's almost no academic research on this subject because the Defense Department is very interested in that. Now, why is that? We talk about these things have a tunable gap, and they're tunable in the infrared range, and so they're ideal for infrared detectors. So the Pentagon is very interested because they use this material as infrared sensors, the night vision goggles for the military. But in Europe, especially in Germany, there's an outstanding group, the very group that discovered the quantum Hall effect at the University of Würzburg. After Klaus von Klitzing graduated from that university, they invested in the investigation of mercury telluride quantum wells. And the technology has become so good that they make very high mobility samples of the order of 1 million mobility. And so they have a very small band gap, and so that has a nice feature that usually, so here there are basically in this complicated sandwich structure, there are two main knobs you're going to turn to discover, to study this interesting state. One is the thickness of the quantum well, and we argue this is very important. There's a quantum phase transition. When thickness is less than 6 nanometer, it is boring. When it's greater than 6 nanometer, it goes through a quantum phase transition, becomes this non-trivial state called a quantum spin Hall state. And that is one parameter. So that is tuned by the NBE growers. They just tune how long you shoot this mercury telluride, how long you expose the sample to the bombarding atoms of mercury telluride, and that tells you what is the thickness. And that is one tuning parameter. They do that by growing many, many samples. And once you make this gate structure, you can put a gate between the quantum well and the top metallic gate. And that also has a very interesting effect, because usually the semiconductors that you make are either N-doped or P-doped by adding different kinds of dopants into the system. Now in this case, because the band gap is very small, you can change the carrier type from N type to P type just by changing the gate voltage. And that is only possible in this material system, mercury telluride. So basically, we're ready to do the experiment. You can tune the thickness by growth, and you can tune the doping by changing the gate voltage. So what you expect theoretically is that if you have a boring insulator, you have a conduction band, you have a valence band, you have some intrinsic doping at some fixed chemical potential, and so when you detect the conductance of the system, you obviously will find some finite conductance that are just the type of conduction you see in any semiconductors. So now you slowly change that chemical potential. Now how do you do that? You do that by changing this gate voltage. So in this system, you can change the gate voltage so that the Fermi level light goes from the N-type, the conduction band, to the insulator and back to the valence band. And as you sweep across, you will go through a region which has this gap and there's no state, so therefore there's no conduction. So when you measure the conductance, you will see 0 here. and then the conduction will pick up again once the Fermi level drops into the valence band. But now we argued that so this will be what you expect to detect when you grow a sample which has a thickness of 4 nanometer, let's say. But if you made a sample which has a thickness of 7 nanometer, beyond the 6 nanometer magic transition, you expect this diagram. You will have the valence band, you have the conduction band, you have the valence band, but you have a spin up edge state going up with positive group velocity, spin down states going down with negative group velocity intersecting at this one point. And we argue that this point can never be avoided. So then, if I apply the chemical potential, I will be slowly going through that region from any type through the nominal insulator and then back into the valence band. But here in the middle, it's no longer boring because it has this helical edge state. And as we argued that if you put in a chemical potential on the left to be different from the right, you can lead some conduction. So you will exactly have 2 channels, one on the upper side, and the other on the lower side. So when you measure the conductance, you will exactly see a conductance plateau as a function of the gate voltage at 2 e squared over h. So that's the theoretical prediction. And very fortunately, less than 1 year after the proposal, there's another smoking gun prediction. And we said that you have a conduction band, you have a valence band, you have these edge states, and they have to cross if there's time reversal symmetry that protects them. Now, what if you break the time reversal symmetry? So this is kind of a natural way to test the signature of it. So then if I apply a magnetic field, then this argument of Kramer's doublet no longer applies. There's no Kramer's theorem in the presence of a magnetic field, in the presence of time reversal symmetry breaking. So in general, a gap will open up. But a gap will open up in a singular fashion, proportional to the absolute value of the magnetic field you apply. Right? Usually, anything in physics which are normally well behaved, always proportional to the square, because that's an analytic function. Absolute value function is not a differentiable function. So that tells you that this state, in the absence of a magnetic field, must be very special, because the magnetic field is doing a singular perturbation on it, causing a gap that's linearly proportional to the absolute value of the magnetic field. And then, so here we had some conductance plateau here. Now, if you put in another knob, we talked about 2 knobs. One is D, the other is the chemical potential, but you can put in another knob, which is the magnetic field. Of course, you have yet another knob, which is temperature, but let's talk about that later. But if you put on this magnetic field, then you see that this conductance plateau will have to drop, because now a gap opens up, and that is really not that different from an ordinary insulator, which should have no conductance at 0 temperature. So then you have activated behavior, and the activation gap has to be very singularly dependent on the magnetic field, proportional to the absolute value, and you expect to see this kind of cuspy behavior. So now it comes to the experiment, and these guys worked very hard, and now they first make a sample 1. So sample 1 has 4 nanometer thickness. And that, according to the theory, should be in the topologically trivial class, and an insulator is really an insulator. So as you sweep the gate voltage from N-type conduction to P-type conduction, here in the middle, you see the resistance is very, very high, or the inverse of it, the conductance, is very, very low. Actually, it's almost within the noise of the experimental measurement. And that is so far everybody has ever expected from an insulator in the absence of magnetic field. You will just have no conduction, period, and 0 conductance, infinite resistance. And then they grow a set of sample which has a width of 7 nanometers. And then when you measure, you see you go from N-type to go into the insulator regime, and you see a conductance plateau. And the value of it is close to 2 e squared over h. And more recent data, they can actually go, they have more data points here. But also another very interesting observation is that this value of the plateau, so what's the difference between sample 3 and sample 4? So they are samples or devices manufactured out of the same semiconductor wafer. So they have the same thickness, but they are samples which have different width. So the two dimension, if you look at Horvath, the width in the two dimension, the width is different. The sample 3 has 0.5 micron width, and sample 4 has 1 micron width. So, but you see that the conductance is independent of that width, and that is a direct violation of the Coulomb's law. Not Coulomb's law, the Ohm's law. Ohm's law basically says that if you make the width wider, the conductance has to be, you have to have more conductance or less resistance, because you put resistors in parallel. But here, the reason, at least we interpreted that they are independent of the width, is that even though you are making a measurement out of the two-dimensional sample, the true conduction is carried by the edge state, and there are only two of them. And no matter how wide or how narrow the sample is, you only have two channels, and you only have 2e squared over h, independent of the width of the sample. So that's the first experiment, and we of course get very excited. And then you measure the dependence on the magnetic field, and you see that as you apply a magnetic field, you can both apply magnetic field along the z-axis, but also slowly rotating into the xy plane. Now, magnetic fields always lead to breaking of time reversal symmetry, which would have a detrimental effect on the helical edge state conduction. But the magnitude-wise, if you put a magnetic field along the z direction, it has a much bigger effect, because here you have both orbital effect and the Zeeman effect, right? Because the magnetic field can both change the orbital degree of freedom of the electron, but also the spin degree of freedom of the electron. And so actually, when you estimate, the orbital effect is 2 orders of magnitude larger than the Zeeman effect. So when you put a magnetic field here, you expect this Cuspy-like drop of the conductance. And here, indeed, you find it, that here it's basically these 2e squared over h conductance now somehow normalized. And then when you apply the magnetic field, you see a drop of the conductance quite sharply. It looks like pretty non-analytic up here. But when you rotate the magnetic field into the xy plane, the effect in principle should still be there, but because the effect is smaller, only has Zeeman effect, no orbital effect, the effect is smaller. So that's exactly what we anticipated from the theoretical understanding. So I'm almost done. Let me just tell you that the fact that this is a topologically non-trivial state leads to remarkable predictions. And in particular, it predicts that in this material, which only consists of integer electrons with integer charge, namely E, you can make an elementary excitation which has fractional charge. You perhaps know, if you know about the quantum Hall effect, you perhaps know Laufin predicted that in the fractional quantum Hall state, the elementary quasi-particle will have E over 3. But in this system, which is more like the integer quantum spin Hall effect, it will already have fractional charge, but it will have fractional charge E over 2. And that's because that we argue that in the sample boundary, you have two states, you have the two helical states, and they are gapless because they're protected by the time reversal symmetry. Now, if you put on a breaking of the time reversal symmetry by putting a magnetization, then you can open up a gap. But if you make a twist of the magnetization, then you can actually, again, generate a zero mode around here. And there's a famous result by a field theorist, quantum field theorist, Jacques and Rabi, back in 1976, saying that such a domain wall will always induce a fractional charge of E over 2. Now, actually, very soon after the Jacques-Rabi proposal, and I believe actually quite independently, solid-state physicist Sushrief and Heger proposed that such a soliton can arise in a material called polyacetylene. And here you can also make a domain wall by the lattice distortion. And so there you would also have such a soliton. Except you have two copies. You have both spin up and spin down. And the spin up component will give you a fractional charge E over 2, but you also have the spin down component. So altogether, in polyacetylene, you don't expect to see fractional charge because of this rather annoying doubling problem. But we just have shown you that this helical edge state of the quantum spin Hall effect has this magic property that it puts half of the degree of freedom on the upper edge and another half of degree of freedom at the lower edge. So it is basically only, it has only two components, it only has one component. It does not have this doubling problem. So here, if you make a mass domain wall, it will indeed create a fractional charge U over 2. So that's very, very exciting because this proposal, it's just one of the most fundamental proposals. Almost everything that came later, even the brain picture of the string theory, depends on these very simple pictures of the mass domain wall. And it's a theoretical prediction, has never been experimentally tested for a very fundamental reason, because of this doubling problem due to spin degree freedom. But here you really see the uniqueness of the helical edge state because it's already half of the conventional degree of freedom. So there you made a soliton, you will really have E over 2. And that is an experiment which we hope will be carried out in the near future. And that really shows why this is a topologically non-trivial state, because it supports fractional charge. So in conclusion, we know now that there are the boring conventional insulators we have been dealing with for the past 50 years, has been tremendously useful for semiconductor silicon industry. But then we discovered the quantum Hall effect that is really a new state of matter. It has conduction band and valence bands, but it has edge states which traverse through the valence and the conduction band. And the number of those edge states is a topological invariant, and that's why the quantum Hall state is an interesting first example of a topologically non-trivial state. And I hope I have convinced you that there's yet another state which is fundamentally different from the quantum Hall state because it has no magnetic field, no time reversal symmetry breaking, but also fundamentally different from any ordinary insulator in the sense it has a pair of helical edge states. Upspin goes one way, downspin goes the other way. They cross, but that crossing can never be removed. And in that sense, that state can never, through a continuous distortion, be mapped onto a boring ordinary insulator. And it has profound experimental consequence, which has now been observed, partially observed experimentally. Thank you.
Thank you very much. And questions? Let's thank the speaker again.